Hi everyone, I hope you're having a good day. I especially hope you're being nice to my sub. Welcome to my first attempt at a video lecture. After I'm done recording this, I'm going to upload it to Google Classroom, so you should have free access to it to replay, rewind, pause, whatever you need, so it'll be there for you. Before we get started, I just want to take a minute to review the last couple of days in class. A couple days ago, I introduced you to the idea of forces. We defined forces. We talked about the units that we measure forces in. That would be newtons. We also explored the idea of a free body diagram, also known as a force diagram, which is going to be incredibly important, as you can see from this intro slide. I talked about Newton's three laws of motion. We focused in particular on Newton's second law of motion. That was sigma F equals ma, or the sum of the forces on an object are equal to an object's mass times an object's acceleration. And we also defined mass and weight, talked about the units for each, and distinguished them from each other. Mass we described as being how hard it is to accelerate an object, and weight would be the force of gravity on an object. Today, I'm going to focus on free body diagrams. Now, if you've looked at the learning set, you realize that I think it's the first 5 problems that you have to solve only ask you to do free body diagrams and reality sketches, no calculations at all. So, free body diagrams are really important for starting the learning set. They're also important for doing well on all of the learning set, and they're going to be crucial for doing well on the unit test in a week and a half. So today I'm going to go ahead and walk you through 3 example free body diagrams. Okay, we're going to talk first about objects in free fall. Then I'm going to go ahead and talk to you about objects falling at a constant velocity. And then finally, we'll talk about objects moving horizontally. All right, so let's go ahead and get started. Before we do any free body diagrams, I think it's important that we review Newton's first law of motion, which is also known as the law of inertia. Now, if you look it up on Wikipedia or Google, it's going to say that an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an unbalanced force. This is an absolutely true statement, but as it's written, it doesn't really do me a whole lot of good, or doesn't do us a whole lot of good in physics class, so I think we need to unpack the definition and really kind of figure out what the implications are for forces acting on objects. The first would be that if an object is at rest, so if you're reading a problem and it says that an object is at rest, sorry about the bad handwriting, I'm going to work on improving it, then that means that the forces on the object are balanced. Okay, so if an object's at rest, it means that all the forces acting on that object are balanced. Okay? If there's an up force, there's an equal down force. If there's a right force, there's an equal left force. The same is true for an object that has a constant velocity. If an object is moving and it's not accelerating, if it has a constant velocity, then the forces on that object are also balanced, just like an object at rest. Okay? So the key is we're looking for acceleration. However, if an object is accelerating, then that means that the forces are unbalanced forces. So that's going to be the key thing. If it's at rest, or if it has a constant velocity, then the forces are balanced. If it's accelerating, then the forces are unbalanced. Okay, so with those 3 things in mind, let's go ahead and run through some quick examples. I'm going to start with an object falling. When an object falls, such as, I don't know, a physics textbook thrown by a diligent physics student wanting to demonstrate acceleration due to gravity, problems will often state that that object is in free fall. And what this means is that it's accelerating downward with an acceleration of 9.8 meters per second, which you know from last unit. That's the acceleration due to gravity. And we tend to negate air resistance or friction or anything. So really what we're saying is that there's the force of gravity on it and nothing else. Okay, so it's accelerating, the forces are unbalanced. That means that there's only the one force of gravity and nothing else to counterbalance it. So whenever we draw a motion diagram, we always start out with a single dot. That's going to be the object of interest. In this case, it's going to be a book, so I'll label it B. And then we draw a force arrow. And remember, these are called vector arrows, force vectors, whatever. So we're going to have an arrow to demonstrate the force of gravity on the book. So that'll be pointed down. And we need to label the arrow F for force. And then we need to specify that it's the force of gravity, G-R-A-V. Okay, and I'm not that particular. You can label it any other way as long as it's clear, on the book, the force of gravity on the book. Now, because that book is accelerating, we know that there's no force upward counterbalancing that. So this is about as simple of a free body diagram as we get. So I'm going to label this physics diagram. You might take the time to draw this reality sketch or something similar. And one last thing that I do want to add, and I think you should get in the habit now of adding these, although it doesn't really matter unless you're doing calculations, you should assign a positive direction. In this case, because the book is both moving down and accelerating down, I'm going to make down the positive direction. So if we were to do calculations, our numbers would be mostly positive, which would make more sense. Okay, I hope I'm not rushing too much, but let's move on to another example. What if something is in free fall, but it's no longer accelerating down? Last unit we talked about the concept of terminal velocity. That's where an object is falling down due to gravity, is being pulled down by gravity, but has accelerated up to its maximum velocity. So here's my reality sketch. It's me jumping out of an airplane. I'm accelerating until I hit terminal velocity. Now, terminal velocity means that the force of the wind is equal to the force of gravity. So in this case, just like in the last example, I'm going to draw a dot to represent the object. That's going to be Mr. Bennett. All right, so I'll say Mr. B. And now I'm not accelerating. I've hit terminal velocity. And terminal velocity means that it's a constant velocity. I'm no longer accelerating. I'm going as fast towards the ground as I possibly can. So if we go back 2 slides, constant velocity means that the forces are balanced. The constant velocity means that the forces are balanced. So here I am, Mr. Bennett, and we know that there's a force of gravity acting on me. That's a downward vector arrow. That's going to be the force of gravity on Mr. Bennett. But we also know that at this point the wind is rushing up against me so much as to slow me down, or not slow me down, but prevent me from accelerating further. So there's an upward force of, I don't know, let's say the force of wind or air. So I'll say the force of air on Mr. Bennett. Okay, so the forces are balanced. I'm not accelerating. All right, and that means the force going up due to air and the force going down due to gravity are in balance. Again, I need to set a direction. I may as well say down is positive because that's the way I'm going. All right, hope everybody feels good with this. Let's move on to the third and final example. Okay, so in this example, it's very similar to the other ones, except that instead of vertical motion, we're talking about horizontal motion. So we have our reality sketch. This would be 2 stick figures pushing a box and yelling at each other. All right, so in this case, we're going to follow suit. We're going to have do the same thing that we did with the other examples. We need a dot to represent the object. In this case, it's a box. So you can label it B, keep it simple. Now both stick figures are pushing or pulling in the same direction. That means both forces are acting on the box in the same direction. So we have, I don't know, let's say this is going to be person X, and this is going to be person Y. Okay, so on the box, we're going to have two vector arrows. We'll have one here, and I'm going to put one right below it. Okay, so they're side by side. Now there's a couple ways of drawing these vector arrows, but I think this is the best. I'm going to make my dot big enough so that it's obvious that both forces are acting on the box. Now the first arrow would be, I suppose, the force of X on the box. And the second force would be the force of Y on the box. And that's it. Except, of course, off to the side somewhere, go ahead and assign a positive direction. I think it makes the most sense to have the positive direction, the direction that the box is actually moving. Now, is the box accelerating? In this case, we have no idea. We can assume that it is. Imagine these two kind of start pushing a box from rest and it speeds up. In that case, the forces are unbalanced, so the forces to the right are going to be bigger than the forces to the left. If they're at a constant speed, then you might be able to add a third force, okay, which would be the force of friction or the floor on the box. Okay, so if the box is at a constant velocity, if they're just moving along at 2 meters per second, then the force of the friction or the friction of the floor on the box would be equal to the forces of X and Y on the box. All right, today I'm not going to get into calculations. I'm going to save those for maybe a similar lecture on Monday. I want you to spend the next, I guess the rest of class working together in small groups or individually, help each other out. I want you to get through questions 1 through 5 in the learning set, so that'd be the first 2 groups of questions in the learning set. They're the ones that just ask you to do free body diagrams. Again, free body diagrams are incredibly important for doing well in this unit. Okay, some of the later problems get very complicated, and if you have not drawn a good free body diagram, you will not be able to solve the problem. So take it seriously. Good luck. Message me on Remind Me or on Google Classroom if you have any questions. Okay, guys. Good luck. Have a good day.